Welcome to the Newton's second law experiment. This is an extra experiment which will form a useful add-on to video 6.2 on the equations for Newton's second law of motion. This PDF with the notes will be useful for you to have, and you can find it in the folder called Booklet Parts with all your other information. As you know, Newton's second law is taught in grade 11 as part of Newton's laws, and you can see the prescribed experiment talks about Newton's second law for acceleration versus force. Now, the curriculum does not prescribe acceleration versus mass, but I want to encourage you to do both parts of the experiment. One of the essential skills, which is put with the CAP skills, is direct and inverse proportions. And this Newton's second law experiment is the perfect way to learn them. Direct proportion, acceleration is directly proportional to force. Inverse proportion, it is inversely proportional to mass. Also, doing this experiment, you'll learn lots of very valuable practical investigation skills. There'll be data collection and handling through tables. Two different types of graphs will be drawn and analyzed, and one will have a careful look at which are independent, dependent, and control variables. So this is an experiment to investigate the relationship between force, mass, and acceleration for a moving trolley on a runway. I want to encourage you to do the experiment this way with a falling mass piece providing the acceleration. Quite a few of the textbooks mention doing it with using stretched rubber bands to provide the acceleration, but in practice, this is very difficult to get right and do accurately. So you should know the theory by now, Newton's first law and Newton's second law, which gives us the equation F equals ma. In the notes for video 6.2 and in your booklets on page 42, we have this analysis that acceleration is directly proportional to force. In other words, in the first example, if you have a large force on a reasonable sized mass, we get a large acceleration. In the second picture, if you have a small force on the same size mass, we get a small acceleration. Now notice, in order to investigate the relationship between acceleration and force, we had to keep the mass constant. So mass here would be the controlled variable. Acceleration is dependent on force, which is the independent variable. For the second part of the experiment, we investigate acceleration versus mass. So we have to keep the force constant here. Force is controlled. Acceleration, again, is dependent, and mass is independent. We find in the first case, if the mass is small, the acceleration would be large. The second case, if the mass is large, the acceleration would be small. Now, of course, this is just theory. And as scientists, we would like to investigate. So we're going to do this experiment. And you can see the write-up of the method in your notes. We're investigating 3 variables, but of course, we'll only look at 2 at a time. So this is the experimental setup. A trolley of mass m is placed on a friction compensated runway. That simply means we've sloped the runway enough that the trolley with all its attachments will roll down it with constant velocity. So the component of gravity will balance the frictional forces. It's attached to a ticker tape which passes through a ticker timer. We use that to measure the acceleration of the trolley. Alternatively, a timing apparatus could be used. The trolley is accelerated by a falling mass piece. As it falls down under the influence of gravity, it's connected by a piece of string over a pulley, and as it falls down, it accelerates the trolley to the right. As we've said, this is a much better method than trying to use stretch rubber bands. So it provides a constant force, and the force is just the mass in kilograms times g, the acceleration of gravity. Then we change the values of the pulling mass and the trolley mass to provide different pulling forces and masses. Please note that the mass being accelerated is not just big M, the trolley mass, but it's actually big M plus small m, because the whole system is being accelerated. Now, this is what the experimental setup actually looks like. So here we have the ticker timer, and there's a piece of paper tape which passes through it. Ticker timer makes 50 dots per second on the paper tape as it's pulled through, and the spacing of those dots enables us to calculate acceleration from them. Here is our trolley. The wheels run very smoothly, but there is still some friction, and there's quite a lot of friction from the ticker tape. So we slope the runway, as you can see, to compensate for that friction. And then here's our falling mass piece. You might wonder why it's up in the sky. Well, if we allowed it to fall from there, it would hit the ground too soon, and then there'd be no longer an accelerating force. But here's our falling mass piece. And what we can do is hook different masses on there to change the value of m. So once again, acceleration is measured from the ticker timer. The mass is calculated by adding together the trolley mass and the pulley mass. And then the pulling force is calculated by saying F equals mg for the small pulley mass. As we've said, we will do two experiments. First one, acceleration versus force. The second one, acceleration versus total mass. We're going to analyze the result and draw two graphs. And from our graphs, we hope to determine a mathematical relationship between acceleration, force, and mass. In many ways, we will be repeating what Isaac Newton did to come up with the equation F equals ma. So this is a controlled experiment. The idea of that is very important. When you have three variables, you can't allow them all to vary, otherwise you don't know which one is affecting the other. So just to summarize, in experiment one, we're looking at acceleration versus force, so the total mass is kept constant. In practice, we will do this by moving small mass pieces from the trolley onto the pulley, but keeping them within the system. In experiment two, we're measuring acceleration against mass. So in this case, the total mass changes, but the force is constant. This is very easy to do in practice because we simply keep the pulley mass constant so that the pulling force will be constant throughout the experiment. So let's go to the actual experiment, and we'll start with experiment one, acceleration versus force with a constant mass. So let's have a look at a video we made of experiment one. The experiment will be repeated 4 times with 4 different pulling forces to get 4 points for our graph. So the trolley has a mass of 1 kilogram. We add another kilogram, and then we're adding 300 grams. So the trolley has a mass of 2,300 grams, plus the 100 on the pulley gives us a total of 2,400 grams. You can see that 1 Newton pulling force was very small, and so the trolley moved very slowly. Now we take a second 100 gram off the trolley, put it on the pulley. We now have a 2 Newton pulling force, and you can see the trolley is a little bit faster. For the third one, we take another 100 gram mass piece from the trolley to the pulley. So we now have a 3 Newton pulling force, and you can see the trolley moves a lot faster, and you can see it collides a lot harder. For the last one, we take a last 100 gram mass, put it on the pulley, and then we release the trolley, and you can see with a 4 Newton pulling force, the trolley moves very fast and goes to the other side very quickly. The video is restarted, but just have a look at the first experiment again in comparison with the last one. And remember, with a 1 Newton pulling force, it was very, very slow. So as you saw, whenever we took mass pieces to put onto the pulley, we took them out of the trolley to make sure that the total mass of the system stayed constant. Let's have a look at some of the figures we got from the experiment. So it's very important to watch that video and see what actually happens in the experiment so it can be real. So let's fill in the results on your results table in your notes. So at the top of the table, we put the constant total mass. And as you saw, that was 2,500 grams or 2.5 kilograms. That's not going to change, which is why we put it at the top. That is the controlled variable. We would produce 4 ticker tapes. To save time, we're just going to give you the values we calculated for acceleration, but the experiment is repeated 4 times and with 4 different pulling masses. As you saw, we started with 100 grams on the pulley, then 200, 300, and then 400. Because these masses were taken off the trolley each time, as the pulling mass got heavier, the trolley mass got lighter, but what you should see is that the total of the two is always 2,500 grams. Now, we're just going to approximate G equals to 10 to make the calculations easier. So 100 grams is equivalent to a pulling force of 1 Newton, 200 grams, 2 Newtons, 300 grams, 3 Newtons, 400 grams, 4 Newtons. Now, all of these figures you can copy down. And then, of course, by analyzing the 4 ticker tapes, we came up with the 4 values for acceleration. Now, you'll just have to accept these. These are the values we calculated after doing the experiment that you saw in the video and analyzing the 4 ticker tapes. Now, in this particular experiment, you're going to be graphing acceleration in the last column versus pulling force. So there's our dependent variable of acceleration and our independent variable of pulling force. So please make sure that all of these figures are written down in your table. Then we'll proceed on the next page to looking at a graph of acceleration versus force. So we just need these 2 columns now, acceleration and force, and we're going to draw a graph. Earlier on in our video series, in fact, it was in video 1.2, the introduction to graphs, we introduced you to the TALSUP method for drawing a graph. So just go back in your booklets and revise that if you're not sure, using the acronym TALSUP to actually do the different parts of drawing a graph. So the first part, T, stands for title. Write an appropriate title in the box above the graph. Choose variables for your x-axis and your y-axis. Now we've already decided our dependent variable is acceleration, our independent is force. Then label your axes with units. And then what usually causes problems for pupils is the idea of scale. Now let's start off with acceleration. So acceleration is on the vertical side of the graph. There are 5 large blocks on that vertical axis. And there are 11 large blocks on the horizontal axis. So let's start with the x-axis. X-axis, we have force. You can see it ranges from 1 to 4 newtons. So if we make one large block equal to 0.5, it'll go from 0 to 1 to 2 to 3 to 4 newtons. We want to use up as much of the graph paper as possible. If we look on the y-axis, acceleration ranges from 0.4 to 1.6. So one large block there, if it equals 0.4 meters per second squared, that will fit in nicely. Now we also need to break this down further into intervals. You see each large block has 5 small blocks. So if one large block equals 0.5 newtons, we divide by 5. One small block would equal 0.1 newtons for force. On the y-axis, if one large block equals 0.4 meters per second squared, one small block we divide by 5 would be 0.08 meters per second squared. Then, using the scales and intervals, you will simply plot your points onto the graph carefully. Make sure you don't mix up the x and y coordinates, and then plot the best fit line for the data points, calculate intercept and gradient. So let me help you with the first graph. So the T for TALSUP was for title, and we have a title, graph of acceleration versus force. Always put your dependent variable first. A stands for axes, and we've said on the vertical axis we'll have A, and we must label it L in meters per second squared. On the horizontal axis, we've got force in newtons. Then our scale, we said that we would have 2 large blocks equaling 1 newton and 1 large block equaling 0.4 meters per second squared. Please notice the scales are very different, and please take note of that when you plot your points. Then, having taken note of the intervals, we simply need to plot the points. So I would encourage you at this stage just to pause the video and to take 5 minutes to try to plot those points, to try to draw a straight line graph through that, and to fill in the conclusion here. It would be very useful for you to try that. So just pause the video for 5 minutes now and do that. Right, I hope you were able to do that. Let me show you what your graph should have looked like. So in plotting the points, the first point there, we see force is 1 and acceleration is 0.4. So the point is there on the conjunction of those 2 values. Second one is 2 newtons, 0.8 meters per second squared. Third point is 3 newtons, 1.2. and the fourth point is 4 newtons, 1.6. These were very easy to plot because they fall nicely on the intersections of the large blocks. Then we must plot the best fit line through those, and we can see that the line not only goes through the points, it also goes through the origin. So now we can come to fill in our conclusion. We notice that an increase in pulling force resulted in an increase in acceleration. Okay, so our graph of acceleration versus force was a straight line graph. You can see that clearly, and that indicates that acceleration is directly proportional to force, or in symbols, A is proportional to force. And that fits with what we understand. When you're pushing a car, the larger the force, the greater the acceleration, and the faster the car will go. That finishes the first part of our experiment. So let's have a look at a video of experiment 2, where we're seeing how acceleration depends on mass. Watch closely in this video that the total mass that's pulling here, the pulley mass, will not change, whereas the mass of the trolley will change. So you'll have the same force pulling a trolley that gets heavier and heavier all the time. Now, to start off with, the trolley weighs 1 kilogram, and we've got 200 grams on the pulley, so it's a total of 1.2 kilograms, and you can see the acceleration is quite fast. In the second trial, we add mass pieces so that the trolley will be 2.2 plus 200 on the pulley makes a total of 2.4, and you can see it's slower. The third one, we're going to add to make 2 kilograms, 3 kilograms trolley mass, plus 400 grams, plus the 200 there makes 3.6 kilograms, and you can see the acceleration has really gone down. For the last one, we need to add a lot of mass. 1 kilogram for the trolley, plus 1 is 2, plus 1 is 3, plus 1 is 4. Then we add 600 grams, 4.6 plus 0.2 gives us a total of 4.8 kilos. And you can see the trolley is really slow this time. Now, perhaps let's return to the start and just have a look at the first trial again, just so you can compare and see how fast it was before. So having seen the video of the second experiment, let's take the data down and let's draw the graph in our notes. So under our results, we put the constant pulling mass of 200 grams, which is equivalent to 2 newtons. Remember, we're just approximating G equal to 10 for this experiment to make it simpler. Again, that gets put on top of the table because it's constant and it's not going to change with the different repetitions of the experiment. Once again, being good scientists, we produce 4 different ticker tapes. We repeat the experiment 4 times so we can be sure of our answer. Now, as you saw, what was changed was the trolley mass, and the pulling mass of 200 stayed the same every time. So pulling mass and therefore pulling force is our controlled variable. Total mass is our independent variable. We decided what it should be, and acceleration is dependent in this experiment. So remember, the total mass is the important one, not just the trolley mass. We started with 1.2 kilograms, and it was doubled, tripled, and 4 times. Now, once again, as you saw in the video, we've performed the experiment. We analyzed the 4 ticker tapes, and these were the results, which you will just have to accept and write down. And of course, we're focusing on the last 2 columns in the table. We want to graph acceleration versus total mass. So please copy all these figures into your table. Pause the video if you need more time. We're now going to complete the second graph using these figures here, and we'll find that it looks quite different from the first graph. So I won't go through the whole TALSUP method step by step, but of course, first of all, we need a title, acceleration versus mass this time. We need to label our axes, and again, acceleration is our dependent variable, mass is our independent variable, and don't forget the units. When we look at the values, the range of values, we would put a scale like this so that our 4.8 kilograms can still fit on the x-axis, and our 1.7 meters per second squared can still fit on the y-axis. Now, again, it's a very useful exercise for you as pupils to be able to plot these points. These ones are quite a lot more difficult than in experiment 1 because they don't always lie neatly on the intersections of the large blocks. So you will need to consider the scale and the intercept. Please pause the video here for 5 minutes while you try to plot these points. Draw the best fit line, which will not be a straight line, and then fill in the conclusion. Please try this now. Right, let me go through this with you and let's see if you had everything in the right place. So in plotting these points, the first point there is a mass of 1.2, so it's 1 plus 2 small blocks, 1.2, and on the y-axis it's 1.7. Now maybe you're not quite sure why that is 4 blocks there, but please take some time to consider carefully why that point should be there with your teacher. Second point, 2.4 kilograms is 0.8 meters per second squared. Now we notice that as the mass increased, actually the acceleration decreased. Third point, 3.6 kilograms is 0.5. That lies nicely on the line. It's easy to see. And the last point, 4.8 kilograms is 0.4. Now, if we join these, we get a curve. And in fact, it's a very special type of curve that we call a hyperbola. It's an inverse relationship. So we can fill in our conclusion. We noted that an increase in total mass resulted in a decrease in acceleration, different from experiment 1. Our graph of acceleration versus mass was a hyperbola. That's the name of this graph, indicating that acceleration is inversely proportional to mass, or in symbols, A is proportional to 1 over m. So I hope you saw very nicely in this experiment. In experiment 1, we showed that acceleration is directly proportional to force. And from this experiment 2, we've seen that acceleration is inversely proportional to mass. Although this particular experiment has not been directly examined for many years, it is still a very useful experiment for understanding Newton's second law of motion.